Good afternoon, everyone, and welcome to today's webinar on electronics enclosure design and how simulation can help. Before we start directly talking about the topic, a few technical notes. We're using GoToWebinar to broadcast this webinar today, and you should be able to hear me now, and it would be great if you quickly can indicate that you can hear me. There's a little feature in GoToWebinar that allows you to raise your hand, and if you quickly raise that hand, I can see that it's working great. So that's fantastic. Next up, GoToWebinar allows to ask questions inside this tool. So at any point in time during the webinar, just type in any questions that pops up or any comment you might have. We try to keep these demos very short, that they can be easily digested and that they don't consume too much time. But I'll try to cover as many questions as possible by the end of the demo today. And if I can't cover them, there's also my email address in the slide deck, and so we can follow up on them afterwards. All right. There's also one thing I almost forgot. We also record this webinar, and it's going to be sent afterwards to every registrant so that you can review it again. All right. Then let's directly dig into it. Quick note to myself, my name is David. I'm the CEO here at SimScale. I have a background mainly in CFD. We'll touch today both on CFD as well as finite element-based thermal analysis. So we'll hear more on that later. There you can find my Twitter handle and, as discussed, also my email address. Before we go into the details of today's topic, I really like to zoom out and take a look at the big picture and why we're talking about this. This is an image I recently found on I think it was even on the on some forum or economic forum where they discussed the Internet of Things, and I like this slide because it shows sort of a trend that we're in the middle of it, right? There's many products that are being where more electronics are put into the product to make them smarter. It could be, connecting them to the internet, but then there's also all sorts of machine-to-machine communication, et cetera, et cetera. So there's a big trend in general manufacturing in our industry going on, that products that used to be sort of stupid in the past will become connected, will become intelligent. Consumers, meanwhile, expect that from products, and so as a result of that, more and more electronics are being put into smaller and smaller devices, right? And this is sort of a trend that has been going on for some time, and that will go on, and that is prevalent in our industry today. And so I think this sort of sets the stage very nicely to talk about electronics enclosure design and thermal management around it, right? Because while in the past specific products might not have had all sorts of electronics in there, chances are that over the next years or decade, they also will get hooked up with all sorts of electronics. It's not always, CPUs and heavy compute-intense semiconductors, but everywhere where there's electronics, there's heat, right? And this heat needs to be managed, and we as engineers will need to deal with it. And that sort of sets the stage for this little demo today, or the bigger picture today, because the importance of thermal management will rise through that, right? Smaller devices, smaller products, more electronics in there, less space to dissipate the heat, more, or even the acceptance level to noise of fans, etc., will go down, etc. And all of this combines or contributes to the rising challenge of thermal management, thermal design in electronics enclosure design. And the two examples that you can see on this slide are about sort of specifically show two examples where there is no active cooling in there, right? So a smartphone or a phone in general is a good example of not a completely sealed enclosure, but at least there's no active cooling in there, right? We don't have fans or something jumping on when the phone gets hot. Same here on the right. That's an industrial equipment, a piece of industrial equipment where there was also no fans built in, and that's the scenario we're going to look at today in more detail. And we'll have additional demos where we're also going to talk about actively cooled or not entirely sealed enclosures. But I like to start these to look at enclosure design for looking at sealed enclosure design, because from my perspective, the challenges here are even bigger, right? On the one hand side, we have no option to actively cool. We can't put fans in there, etc., and that significantly limits the number of design parameters or design space sort of that we can use to improve the thermal performance of the enclosure, so to make sure that the chips we're putting in there never pass the temperature limit where they start to fail, right? And a couple of examples can be shown on this slide. So obviously, even in sealed enclosures, there might be a benefit or an improvement to the thermal performance of the enclosure when we put heat sinks in there. And actually, we're going to see an example later today to where that'll work. There's all sorts of thermal interface materials, TIMs, different heat pipes, or different adhesives that I can put on the semiconductors. But yeah, I mean, what's not on this slide, and I think that's more important, is fans, right? So we cannot put something in there that just blows more air over the semiconductors that get hot. And in today's webinar, we like to demo that in a very hands-on manner, and we're going to look at a specific design scenario, at a specific product. I'll quickly want to show that to you here. That's going to be the case or the design scenario that we'll use to demonstrate how SimScale, how FEA, how CFD in general can help in such enclosure design challenges. That's a sort of a PCB board of a piece of industrial equipment that's being used in some industrial computers, and in blue is sort of a very, very simplified PCB board, PC board, and all the other, and in the real design there's lots of other components on here, some various electronics components. But for the design scenario today, we sort of neglect most of them and just look at 3 chips that produce most of the heat. So in this case, we already decreased the complexity of this case and said, okay, we only look at the thermal, at the components of this PCB board that is very, very, that are relevant to the thermal management of this design or of this enclosure. And so this PCB board is put into an aluminum enclosure that we can see sort of here a little bit translucent. We can see the different heat loss of the 3 chips. And obviously there's a couple of design constraints, right? As discussed, that's a sealed enclosure. So we do not have the option of do active cooling or put any fans in here. For some reason, because this backboard is put somewhere into industrial in an industrial environment, the box dimensions are fixed, right? So we cannot increase the sort of airspace that we have in here for some reason. Obviously, I've got some constraint on where my chips start failing. So I have a maximum chip temperature that I need to respect. And last but not least, we want the enclosure temperature, so at the outside, also to remain below a specific value. In this case, not because it's a handheld device, because of some surrounding constraints that we have here, right? We've chosen this design because it's a very it reflects lots of the design challenges that we see customers having and solving with SimScale. And sometimes these types of electronics can be found in some sort of sensor equipment or some sort of sensor box that's being used in industry. Sometimes it's some sort of compute unit for a piece of industrial equipment or a machine, et cetera, et cetera. So there's many different versions of this. But we oftentimes see these challenges. Hey, I have some semiconductors that produce a ton of heat. I have some design constraints for whatever reason that constrain me in how I'm able to cool these chips. And then sometimes geometric constraints, temperature constraints, etc. So I think it's a good scenario to sort of look at how CFD and FEA can help in such a scenario. What we're also looking at here is the baseline design. So that's the initial design, sort of where the engineer said, hey, without doing simulation, this is how I would do this design, and I hope that the passive convection around these chips are sufficient to sort of cool them down, etc. So that's the baseline design with which we'll start. And then afterwards, we're going to dig deeper into design improvements that can be derived from the simulations we're seeing. And this webinar is about using simulation now to do so, right? And so to quickly motivate that, if you do such an enclosure design without simulation, chances are that you keep on iterating initially in your CAD environment and sort of maybe do some hand calculations before you build a physical prototype. You actually do the thermal testing and then have sort of see what type of temperatures you're reaching, right, and whether or not they are acceptable. And in today's world of 3D printing, additive manufacturing technologies, etc., that's actually physical prototyping is something that's affordable, but specifically when it comes to these chips and also the time usage, this can be significant, right? So these loops that you see here, these iterations you can do with physical prototypes are naturally somehow limited because eventually you're going to have a deadline to reach. And so the value of simulation is in doing all of this digitally, right? So you do all of this within your computer. So an initial rough CAD model is enough to spin up a simulation, see what temperatures you're reaching on your chips. You can go back immediately to your design and make improvements accordingly. So the iterations are faster, they are cheaper, and by that you can do more of them. And ultimately that's money in your pocket, right? For whatever reason. You could have saved on prototypes, you could have saved on time, reach your deadline, earlier to market. Ultimately, it's money in your pocket. Few words about SimScale, because today we're going to generally look at simulation, but in specific at how to do it with SimScale. The unique thing about SimScale is that first and foremost, it runs in a web browser, so there's no software, no hardware for the customer to maintain, to purchase, etc. It's really zero hardware, zero software on the client side. From a pricing perspective, it starts even for free. So there's a free community plan that allows you to simulate with all features, with free computing power, but all your simulations will be publicly available and shared with the SimScale community. And then there's basically a low entry price to our professional plans where you can start running private simulation projects, confidential ones. And the great thing is that you can buy additional computing time as you go and as you need it. So the idea is that you always have the simulation capacity that you need and not the one there's some fixed hardware you needed to roll out, etc. So it's a sort of pay-as-you-go pricing model. Last but not least, we want to make SimScale for everyone. We want simulation to be accessible for everyone. And we do so by enhanced collaboration functionality. So you can share simulation projects with colleagues, with our support, with clients. There's a real-time chat available within SimScale where you can talk directly to our support engineers. There's a large community that shares simulation know-how where you can make copies of other simulation projects and learn from them, etc. So the idea is to reduce the level of know-how that's necessary to get reliable results. Here's a little sort of overview over the workflow on SimScale. So that's a real-world example. That's another. That's not the electronics enclosure we're going to look at today, but a similar one. And so here we have the workflow. There's a CAD model that you upload. You can see that this is a web browser, and then you have everything on SimScale to define the simulation, run it in the cloud, and then ultimately also post-process, analyze the results. So here we can see a temperature plot of the different parts. You can see that the heatsink over here gets hot, And then we can also see here a visualization of the flow field through the different components. But we're gonna see this in action in a few minutes. The idea, or the summary of this, is that you bring your CAD model and then you've got everything you need within SimScale to run the simulation, post-process it, and leave basically with your design decision. Everything completely within a web browser. All right, from a physics point of view, there's more in SimScale, but since today we're mainly interested in thermal management, from a physics point of view, here are a few examples that you can do, right? We generally support convection and conduction, and the sort of the combination of them, right? So in the top left here, you can see a coupled convection and conduction analysis. So this, people call it a conjugate heat transfer analysis, right? So we have a fluid entering the domain at a specific temperature, and then the heat transfer coefficient between fluid regions and solid regions is automatically computed. So it's simulated, not constrained. And then, next step is then within the solid also heat transfer is computed, and so ultimately you end up with a temperature field across solids and fluids, and the heat transfer coefficient between them is computed. Here in the top right, that's a gearbox, and that's a pure conductive heat transfer simulation, so only looking at heat transfer in solids. Lower left, another application, conjugate heat transfer, so conduction coupled with convection. And here on the right, a pure convective heat transfer analysis. So that's a fluid entering the domain at a specific temperature, and then via boundary conditions, heat is being extracted from the fluid, and a temperature field is being computed across the flow domain. Overall, SimScale, for some of you might know this, others are new to SimScale. SimScale is not just coping with thermodynamics or thermal analysis, but also classical or traditional structural mechanics that you can see in the top left, and also pure flow simulation. And here we can see a multi-phase flow analysis of a ship as an example, right? So there's, the idea is really multiple types of physics on a single platform within one user interface. All right, but enough about SimScale in general, and let's get our hands dirty and dig a little bit into this particular simulation of this electronics enclosure that we've seen earlier. And before I give you a small walkthrough through such a simulation setup, I want to make a step back and look at different approaches that we could take to run such a simulation. Because ultimately, what we want to end up with, the main concern we're having as an engineer in this case, is the temperature, the maximum temperature of our chips, right? We want them to stay below the maximum, otherwise they will keep failing. So the question is remind me later, all right, sorry for that. The question is this passive cooling approach within this sealed enclosure enough that the temperature for these chips stay below the maximum? And what we could do is basically two different approaches, and both of them work on SimScale. Approach A would be we're simulating both convection as well as conduction. So within the solids, say the printed circuit board, the aluminum enclosure, as well as the other parts in here, we simulate conduction, and then we simulate as well the convection in the air enclosed in here, right? And this approach means that the heat transfer coefficient from the chips to the surrounding air is actually being computed and simulated for, right? That would be approach A. Since we're solving within the flow field as well as in the solid parts, this is a slower approach than approach B. We're going to take a look at that one in a second. But it's also accurate or more accurate than approach B because we're actually solving for the heat transfer coefficient between solids and fluid regions. And that you can see here, right? And we're going to do a little walkthrough through the results in a second in more detail. So no need to study this in detail. Approach B is saying, okay, we're for the time being, we do think that the air in this enclosure, we assume it to be, perfectly steered. It's perfectly steered reactor. Temperature is homogeneous across this. Velocities are, I neglect them, the differences. And I assume a constant heat transfer coefficient from the chips to the air in the enclosure. This means that I'll only simulate conduction, and the effect of convection is basically being constrained. So I'll give it to the simulation as a boundary condition. That's very fast because it's an easier simulation, mathematically not as complex, but less accurate, right? Because I'll assume a constant heat transfer coefficient across the chips. And what we see customers oftentimes doing is saying, okay, I'll use approach A to sort of for the late stage validation when I have a rather converged design and a design that I'm thinking about putting into production, or at least going into physical prototyping. And they use approach B for fast and iterative design, where they say, okay, it's not that important that I'm super accurate. Trends are enough. And what we'll do today is I'll demo you SimScale with approach B and show you a little bit how such a conduction analysis is set up on SimScale. And overall, we're going to do result analysis with approach A and approach B. But you'll see that in a second, right? Fundamentally, it's important that SimScale supports both. You can do flow simulation, you can do structural simulation, you can simulate convection and conduction and coupled, but it's up to you how you want to, which effects to take into account and which not. All right, then we'll quickly jump out of the presentation, open up a new browser window, and quickly browse to simscale.com. And on SimScale, so for the ones that do not yet have a SimScale account, simscale.com, and it's rather simple. Let me quickly log out. So you go to simscale.com, and in the upper right, there's a sign up button, and that allows you to create an account. It's for free. You can start in the community plan. If you want to do confidential projects, then it starts, the paid tiers start. And if you have an account, you go to login. And let me quickly go in there. And the first thing you'll see is your dashboard. I'll not go into details here and directly open up our prepared project. As we'll try to keep these demos to 30 minutes, I just want you to, I'll just give you a rough walkthrough through the simulation setup. So we won't do the entire simulation from beginning to end. Rather, I want you to have a sort of a look and feel flavor for how SimScale works. And then if you're, if you want more details, then you can just create an account yourself. This project is publicly available, so you can review it yourself in more detail. All right, let's quickly look at this approach B that I said, right, where we neglect convection and only look at conduction. So what I did is basically I modeled this up. This is the enclosure. Let's quickly hide the enclosure. Oh, sorry for that. This is the printed circuit board, right, with my 3 chips on there, and I have the enclosure around. I could have modeled this, in a local desktop CAD software such as SolidWorks, or a cloud-based solution such as Onshape. And we support various formats for import. So you just either export it from your desktop software and import it into SimScale, or from a cloud-based CAD system, you can directly import it without download. And so what we'll do as a first step is generate a computational mesh for it. SimScale automates that very much. In this case, here, just that you see that once. So this is basically a computational grid that we generated. We support, there's various algorithms on SimScale. And then the important or the interesting stuff is done over here in the simulation designer. And let me quickly walk you through this analysis. That's basically the conduction only simulation setup. And as a first step in SimScale, you always choose an analysis type, right? And you do that here. So you can see there's various analyses possible: fluid dynamics, solid mechanics. We've done here a heat transfer analysis. I won't change that. And once you've chosen an analysis type, then here on the left under Navigator, a simulation tree is populated that allows you to specify the physics of your setup. And the most important things are basically here on the materials. So we can see that I have I've chosen a material of the PCB. I've chosen silicon for my chips. You can see always in the viewer highlighted where this material is assigned, right? I chose aluminum for the enclosure. Next up, I've basically got 5 different heat loads. I've got a 10 watt, a 7.3 watt, and a 5.5 watt chip. I've got a inner convection. We'll talk about that in a second, what this means. And I got an outer convection boundary condition. And this is an important step. Inner convection, you can see that I'm saying, okay, I assume my reference temperature inside the sealed enclosure to be roughly 320 Kelvin, right? Or a little bit less than 50 degrees Celsius. Again, this is now a constraint, so the simulation won't solve for the temperature inside of the enclosure. So we are constraining the simulation, and I need to know what I'm doing here, right? And I'm going to show you in a second how we can validate this. But in this setup, we're constraining the reference temperature. And also from looking at different tables, there's books where you can look up these values. We're saying the heat transfer coefficient inside between my chips and the air in there is 5 watts per square meter in Kelvin. This is important information. I'm going to see in a second why. Outer convection, I can say that with more confidence. I know I have roughly 300 Kelvin out there, so 27 degrees Celsius, and roughly 10 watts per square meter in Kelvin heat transfer coefficient. And that's effectively it. Afterwards, I can run this simulation, and as a next step, I can also do result visualization inside the browser. Maybe one thing that I wanted to show is under simulation control, the beauty of the cloud is that you have as much computing power as you want, right? You can choose between different machine sizes, specifically for flow simulations that are more compute intensive. That comes in very handy, right? Because you can choose none of the simulations, none of the computing is done on your machine. Everything happens in the cloud. And so this is now a result visualization of the temperature field of my conductive analysis, right? So I can see chip 1, chip 2, chip 3. Chip 1 looks like the hottest, somewhere at 425, 427 Kelvin, which, I mean, we're going to discuss that in a second, which is significantly too high, right? Most chips sort of, go up to 90 degrees Celsius and maybe have peak loads that they can survive, but in our design scenario, we're shooting for less than 90 degrees Celsius, or 370 roughly Kelvin. So this is already, we're seeing this is too high. And I can rotate that and take a look at heat fluxes, etc. But what I wanted to show is sort of the complete walkthrough from CAD model that I uploaded up here, right? This was my CAD model, and then I generated a mesh, set up the physics of the simulation, and then do post-processing over here. So end-to-end simulation workflow inside the web browser. All right. So much for this project. Again, that's a public project, so you can just go to simscale.com/projects. I'm also sending it around afterwards and review the setup in more detail. But now we want to concentrate on, okay, what do we do now with this information, right? What we've looked at, the simulation setup we've went through was approach B, right? Only conduction. What I want to do now in the last 5 minutes of this demo is sort of giving you a feeling for how our customers typically use SimScale in such a scenario. In a first step, they might run actually a fully fledged conjugate heat transfer analysis. So they also look at flow simulation inside the enclosure, and that was being done here, right? It's the exact same design, the 3 chips here again, right? And with the difference that not just conduction in the solid parts is being simulated, but also convection inside the enclosure. And here we can see streamlines of the velocity field, right? And it's what we would expect. One thing to note, this is also the orientation of the enclosure, right? So we're basically looking at this basically to the top, or gravity acts to the bottom of this slide, right? And this is also why we're seeing these buoyancy effects. So the chips heat up the air in front of them, and they then rise because of buoyancy effects to the top, and up there they transmit the heat to the enclosure. It cools down, and sort of this vortex or this air movement inside the enclosure starts happening, right? So we're looking at velocity of 0.15 meters per second, so very low velocity, but still decent cooling that's happening here. So I'm getting some cooler air again to the bottom, and then it rises again and cools the chip. Here's another visualization of this. So this is a cut section view of the velocity field. So we can see the highest velocities in front of the chip, and then above it, due to buoyancy effects. This is a glyph visualization that indicates also the flow direction. And yeah, that's a third visualization where we're looking at the temperature field of the solids and then the velocity field as slice plots in front of it. And again, we can see this buoyancy effects and the resulting temperature from it. So the important information now here is, it's basically two things we're looking at. The first one, the chips are too high, right? We're looking at 90 degrees Celsius max temperature, and we're significantly beyond that, somewhere at 150, something like that, right? So it's too high. The second thing is that our chip 1, so the one here in the lower right, is the one that gets the hottest. And it might be due to the fact that also here convection is not as effective, right? Because I don't have this big vortex structure. I don't have this big area where air can be cooled down again. The second information we're looking at is we can now compare approach A and approach B. Approach A was we modeled convection in combination with conduction, and so we actually solved for the heat transfer coefficient. Approach B is we're only looking at conduction, and we're constraining the convective effect. And interestingly enough is that the results are very similar because I used approach A to tune approach B, right, to approximate the heat transfer coefficient very well. And so the beauty of this is now that for the actual design work, I'm simply going to stick to conduction-only simulations. And so I can combine the confidence that I have in my simulation results from approach A with the speed of approach B. And that's sort of what I'm going to do next. So I'm only going to stick to approach B, to conduction only, for the design work ahead of me. So looking at some iterations. Summing this up, we've got approach B results here. Our max temperature should be somewhere, 90, 80 degrees Celsius, something like that, 90. But we're actually north of 150 for chip 1, somewhere 140 for chip 2, and 130 for chip 3, something like that. And so when we go back and look at the temperature field again in a cut section through the hottest chip that you can see here on the right, we can see that conduction into the PCB is not very good, right? And printed circuit boards are known for that. And so we sort of need to find a way how we can transport more heat faster away from the chip, right? And surprise, surprise. So our first idea is, right, we're going to put some heat sinks in there. So we'll put a very simple heat sink, 3 of them on each chip, or 1 on each chip. And the third idea that this engineer had was we're using a heat pipe to accelerate it even further, right? Just to look at some additional designs. And we'll run simulations again, right? It's as easy as that. And so to quickly compare these, given we're running out of time, so we can now basically do the exact same thing in a web browser and compare very quickly these design versions. So on the left, we can see our baseline design, right, with the chips that got too hot. On the right, we can see that that the heat sinks on the one hand side help us to increase convective heat transfer because we're increasing the area between the solid as well in the air region. Plus, we're going to use them effectively as heat bridges to the top of the enclosure. And so we can see that the overall enclosure gets hotter, but also the chips cool down. And already here, we reached the limit of 90 degrees Celsius. Here we can see heat flux. Again, we'll design 1 compared with design 2. We can see that we've increased heat flux. That's what the heat sink does, right? And we can see that the top enclosure is utilized more to get heat faster away from the chips. And then a quick look at design 3, just, to sort of do same old, same old. You could now look at many different design versions. And that decreases the temperature slightly, but not a lot. Same with heat flux. So we can see that we further increase heat flux, but the temperatures, don't go down a lot. And so putting all of this sort of together means that design 2 with the heat sinks already brought us down below the 90 degrees that we were shooting for. And the heat pipe, the design 3 increased that further, but it was not super effective. Again, this is not about best practices of electronics enclosure design, but rather about how to use simulation, right? The important takeaway here is that we could simulate this very, very quickly within, a few hours of engineering and computing time. We have reliable results where we can see what our chips end up with, what max temperature, and whether or not the cooling is efficient. Bottom line here is that, overall, here are the numbers. 2 hours of manual time for setup and running these simulations. Since we can run everything in the cloud with remote computing power, it was just 3 hours of computing time, 60 core hours, so not a lot. And ultimately, we can, before going into prototyping phase, before going to production, we can simply use these insights into how our designs perform, understand if they don't perform, why they don't, so what can we improve, where are limitations or getting ideas, what we could improve, then improve it and validate whether or not the improvement is sufficient and move on. Before I look at some questions, basically, if you found that interesting, if you're saying, hey, that's something I want to dig into, as I said, SimScale.com, and within 30 seconds, you've got an account and you can look at this yourself, right? And maybe test it on your own designs, or there's hundreds of thousands of public projects that you can use and review what other engineers have done in SimScale. So it's really easy for you to sort of see whether or not this tool is of value for you. And with that, I say thank you. Thanks a lot for the attention. I'll go through some questions if there are any. Let me see. So there's a bunch of them. And in the interest of time, let me answer one of them, and then I'll take the rest via email. One registrant asks if we're neglecting natural convection in approach B. Let me quickly go back to the results. Here are the two next to each other, right? This compares approach A with approach B. In approach B, are we neglecting natural convection? We're not. So the short answer is no. But the longer answer is we're not accurately computing it, right? We're not simulating the velocity field and, turbulence that arises in front of the chip, and how the air moves exactly, when it cools down, how it moves back, etc. So in approach B, we didn't neglect natural convection, but we didn't compute it. We simply constrained the system or the problem with it. So what we're saying is effectively, hey, on these chips, we're assuming the following heat transfer coefficient, and we're assuming the surrounding air to these chips to have the reference temperature of, in this case, 320 Kelvin. And so that's what the simulation is going to do. Whether or not these parameters or these values are accurate or let's say sufficient for your design work or for your engineering work, that's up to you, right? If you're unsure, and that's what we're seeing oftentimes with customers, if you're unsure about these values, you can run a fully fledged conjugate heat transfer analysis where you actually simulate and solve for the convection as well. And from that, you know, okay, what heat transfer coefficient do I have, and can then basically use this as an input to your approach B. But I hope that made this question clear. But the short answer is no, we're not neglecting it because it's important. Otherwise, the chips would even be higher, right? Let's see if we can answer another question. So there's one question, short one that we can answer. There's one question about validations and comparisons. So yes, the question is, has SimScale, are there any validations or comparisons with other tools or results? And the short answer is yes, there are. Under simscale.com, there's a section under learning that says docs, so simscale.com/docs. And here on the validation cases, you can find a couple of them. These are not all of them, but these are some published cases where we publish specific validations known to, you know, against some benchmarks. And the great thing about all of these cases is that even the simulation project where the simulation has been done is actually also publicly available. So you can really drill down in detail and see how the simulation was done. So yeah, the short answer is yes. So there's a couple of more questions, but in the interest of time, I would suggest that we'll wrap up the webinar here. And I promise that I'll follow up on the individual questions with the webinar participants individually. And for the rest, if there's another question popping up, or you're saying, hey, this would have been interesting to know, my email address was in the webinar, and there's also a very active forum on simscale.com that you can engage with, and I encourage you to do so. All right. Again, thank you so much for joining today, and I hope to see you soon on SimScale. Bye-bye.